All right, so this video is going to focus on Graham's law and just the rate at which gases are able to travel. So diffusion is the equivalent to the rate of mixing of gases, having them interspersed with one another, and effusion is having the gases be able to move from a tiny space in their container into an open environment. So Graham's law is going to focus on that effusion piece, and it is basically indirectly proportional for a pair of gases to their molar masses. Now, their speed is going to be directly related to their rate. That's what the rate is measuring. And so if you think about that kinetic energy equation and root mean squared velocity, if you're comparing the two gases to one another, the only variables that would remain would be their molar masses. So taking the square root of the inverse of their molar masses will correlate directly with the rate of one gas compared to a second. And because rate is measuring the change, and in this case, the change in movement over time, when you're looking just at times, it would be directly proportional to their molar masses. The heavier your gas is, the longer it's going to take to effuse. The lighter your gas is, the less time it's going to take to effuse. So here we have a gas whose rate of fusion was measured to be 24.0 milliliters per minute. Another gas under the same conditions, this one's methane, had a rate of effusion of 47.8 milliliters per minute. So it had a quicker rate. What is the molar mass of your unknown gas? It really doesn't matter which one you set as 1 and which one you set as 2, as long as you know which one you have labeled as 1 and which one you have labeled as 2. I'm going to let the unknown gas be 2 in this scenario because that way when I'm solving for my molar mass, I'm going to be solving for x over a number instead of something over x. Just in terms of the mathematics, it's going to make my life a little bit less painful, or at least how I tend to see things. I like them direct. So I'm going to take the rate of gas 1, which was my methane, and divide it by the rate of my unknown gas, and then I will set that equal to the square root of those gases' molar masses once they have been inversed. So methane, 1 carbon, 4 hydrogens, has a molar mass of 16.05. And so if I do my math through and I take the square of both sides of my equation and then multiply by 16.05, I get that the molar mass of that second gas was much heavier, which would make sense given it was not able to travel as quickly, 63.7 grams per mole. So if it took 12 minutes for 1 liter of argon to effuse through a porous barrier, we want to know how long it would take 1 liter of nitrogen to effuse under identical conditions. So we're looking at the times and we have the same amounts. So we can either do the rates and divide it by the time, or we can just use the relationship that we know that time, how long it takes for the gases to effuse, is directly proportional to the square root of their molar masses. So in this case, because I want to know about nitrogen, I'm going to, well, I guess I didn't, sorry. We're going to let nitrogen be gas 1, and we're going to let argon be gas 2. And so if I take the square root of their molar masses, we see that nitrogen has a slightly smaller molar mass than argon, about 3/4 the size of that molar mass. So we would expect it to be able to effuse more quickly, that it would take a smaller period of time to be able to move through. And when I get rid of those units, I take the square root of my molar masses and then I solve for x. I get that it was slightly less, it was only 10 minutes.